The next talk is by Cyril Banderier, and with a few other well-known people to this audience. It's about composition schemes, sorry, q-enumerations and phase transitions in Gibbs models.
Okay, thanks a lot to the gentle organizer of the meeting. And indeed, it's a joint work with this clique of friendly Austrian people. So Stefan and Michel, which are in the room, and Marcus, which is online.
Oh, you have to use the mic. Yes. Thanks, audience.
Blah, 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 blah. Okay. So I was saying that indeed it's a joint work with those friendly Austrian people, Marcus, which is online, and Stefan, which is, hello, Stefan, and Michel, which is Michel Valmer. Okay, so what is it about? Let's begin with a question by Christian Krattenthaler years ago. So he was considering some objects which are called watermelons. I will explain more in details later, but just some big paths which are not crossing. And you consider the number of X contacts with the lower big path with the X-axis. Okay. And you are counting them with a Gibbs weight, Q to the number of contacts. And Q is a real number, exactly like in the previous talk by Zephyr. And so, question, or observation by Christian, realized that the asymptotics of these objects were completely different depending the value of Q. For sure, you can feel it a little bit already, because if Q is 0, so Q to the number of contacts, if you have a lot of contacts, okay, the weights of the objects with many contacts will be almost 0. So Q equals 0 means you forbid the contacts, more or less. And if Q is small, you almost forbid the contacts. On the contrary, if Q is large, then you give a big weight to those objects having a lot of contacts. So it could be expected that indeed, between Q smaller than 1 and Q larger than 1, there will be a different behavior. And Christian was asking, okay, and for sure, in analytic combinatorics, you guys, can you tell me what is the limit to bearing this? So first, for this problem, there is no clear decomposition. There is no clear context-free grammar to tackle these objects. So perhaps that the model could be too hard to be solved. But it was not too hard for Christian Krattenthaler, who came with this nice matter of taste, huge product formula and so on for this number of objects. And from this formula, it's possible to prove that the phase transition, in fact, there is one phase transition, and it is at Q equals 2. And it's not clear a priori why Q equals 2. Q equals 1 could be natural, but Q equals 2, not clear. So in this talk, we will analyze this type of phenomenon, what is the universality behind it, and we will give the limit laws. Okay. So this idea to give a Gibbs weight to the objects is for sure something which is classical in statistical mechanics. And here you have the founding father of statistical mechanics. So Maxwell, Gibbs, and Boltzmann, all of them will play a role later in the talk. And the last image here is the book by Gibbs, which created the name statistical mechanics. So it was elementary principles of statistical mechanics. And in it, for sure, they play with the partition function, which is just this sum here, okay? And up to a change of variable, for sure, it is, you can recognize or generating functions. And so with these objects, you consider some phase transitions in the different objects, model, processes, so on. And by phase transition, the classical definition could be that if you move in a continuous way a parameter, if you move a parameter in some analytic way, suddenly you will have a macroscopic change of behavior. So another way to see it quite often is that, okay, in fact, you have a singularity on your generating function. This will detect phase transitions. And indeed, this is exactly what we will have in our examples after. Okay, so let's give a more rigorous definition of what will be your model. So for a family of combinatorial objects, we have some parameters that we will count on them. So the statistic here. And we are counting the number of objects of size n with a weight which will be q to the k when you have the statistic as value k, and you renormalize so that you get a probability distribution. So this is, for the people online, this is formula for sure, okay? And you can rewrite it in different ways. This is the model of the Gibbs distribution. So in physics, quite often, Gibbs distribution, Boltzmann distributions, they are used as synonyms. It's convenient to do a distinction between both of them. And I will comment on this a little bit later on the slides, but just one remark. For sure, when you have q equals 1, this is the classical model of the uniform distribution. Okay, very easy. This model also was for some objects, for example, for permutations. So the famous Mallows distribution model on permutation is exactly this model when your statistics is the number of inversions, so very old model, more than 50 years ago. And for sure, to analyze all those stuff, we will consider the following bivariate generating function. Okay, but q here is a real number. So it shares the spirit of the Boltzmann distribution that Zephyr mentioned before. But however, I will make a slight difference between what I will call the Gibbs distribution, this one, and the Boltzmann distribution. For the Boltzmann distribution, and it was the key idea in the famous article by Philippe Duchon, Philippe Lajolie, Guy Louchard, and Gilles Schaeffer for doing some uniform random generation of conjugate structures. Their key idea was that in fact, you will give to each object a weight, which is this weight here, in which you normalize not by the number of guys of a given size, but by everybody of any size. So you kind of mix different sizes together. And at the end, when you run your algorithms, you give some values to this k and z, such that the distribution, the shape of this will be concentrated on the n and the k that you want to reach. And so you see here the difference between Boltzmann and Gibbs. This is a slight difference, so they are not exactly the same. Okay. So for sure, the change of variable, which I mentioned before to make the link between the partition function and the logarithmic function, will be this change of variable. And quite often in statistical mechanics, T can be seen as the temperature of the model. And Kali, so here you have a glass of water. So if T is 0, then you are kind of freezing your object. So this is the solid phase. And quite often in this case, you get a discrete distribution. We will see it in our example later. On the contrary, if T is very large, you get some gaseous phase and quite often a Gaussian distribution. And the place, the critical value where happens something is this TC, where you get something which is a liquid phase. And here you have an illustration from the book Where the Wild Things Are, which was written and drawn by Maurice Sendak to illustrate a little bit the idea that indeed on those locations we get some fancy distribution, fancy characters which are not at all Gaussians. Okay, so we will consider those models for combinatorial objects which are counted by compositions. Okay, and for sure you have a lot of objects in combinatorics which can be by composition of functions. So random walks, Polya-Ernst, Galton-Watson processes, trees, permutations, random mappings, set partitions, interpolations, tunneling graphs, maps, like we saw just before. And so let's say that the type of schemes that we will consider is those type of generating functions. So objects which are counting by a scheme of this type. Okay. And when you get such a scheme, where is the radius of convergence? Where the singularity could come from? So you start from 0, you increase z. So we have positive coefficients on all those guys, they are counting stuff. So there is a theorem, the Prince-Stein theorem, which says that the singularity, if any, will be on the real positive axis. So you start from 0, you increase z. And when you could have a singularity, okay? Perhaps that M could be singular before G of H. Okay, but then it's kind of stupid classical analysis. Enfin, not stupid, but classical and well done in the book by Bob and Philip, analytic combinatorics. Or you could first have H, which is singular, and all the rest regular then. Okay, and then also it's easy and well understood. Or you could have a fancier phenomenon, which is that when Z is reaching the singular value of H, this guy reaches a value which is a singularity of G, and at this location, M could be or not also singular. And when you have this, you have a kind of composition of singularities, confluence of singularities, and this is where you have interesting phase transitions. Okay, and then the scheme is called critical. Okay, so here you have some examples of critical stuff, and if it is not critical, you have a lot of tools. All theorems by Bender, and many people in the room consider schemes which are not critical. Some observers later consider critical schemes. I will comment on this later. You could approach this by methods from analytic combinatorics, or also by more probability theory approaches, like in this book by Barbour, Tavare, and Aradia. Okay. So different objects which can be counted by composition schemes. And then the parameter, if you count the number of structures H, so you put a parameter here, for example, then you get some statistics which are a sum of random variables which are almost IID, but not really. And because of this, you don't necessarily get Gaussian distributions at the end. You get, most of the time, you will get non-Gaussian distributions. Okay. So if you count the number of structure of H components, when you have the uniform model, this is what I presented at the last AofA, and I briefly recall it because I will use it later. So the generating function is this one. We consider the case of function H and G and H and M, which have a Puiseux expansion of this shape, where tau H, CH, and rho H, lambda H will be different for G, H, and M. Okay, and what happens is that when you have such schemes, the limit law is strongly depending on this critical exponent here. So if this exponent is smaller than 0, then we are in the supercritical case, so you get some Gaussian limit laws. If you are between 0 and 1, then you get some generalized Mittag-Leffert distributions. This is what I presented last time. And if you are between 1 and 2, then you get some limit distributions which are related to stable laws. This was also mentioned in the previous talk. Okay. And when lambda H is larger than 2, this is Gaussian again. So the interesting cases which are partially open, which were partially open, was there. And this is what we filled in the last AofA, where we proved that when you are in such cases, what you get, well, it is splitting into 3 cases, depending on the relationships between the critical exponents, the Puiseux exponents of the different functions. If you are in this case, you get a generalized Mittag-Leffert distribution. In this case, you get a linear sum of a continuous distribution, the Mittag-Leffert distribution, and the discrete distribution, the Boltzmann distribution, and in this case, Boltzmann distribution. Okay. So now, if we apply those ideas to the Gibbs model, what it gives. So first, a little lemma. So our Gibbs models, for example, let's consider these compositions, where no Q is a real number. So Q being a real number, what it gives what Michel Rota in his talk called a movable singularity. You move where could be you move the radius of convergence in one sense, and then you get quite often interesting phenomenon when you do this. So you have different, so there is a critical Q such that the scheme will be critical in the sense that we defined before, and below it, it will be subcritical, above it, supercritical. And in these 3 different regions, you get different type of asymptotics, okay? And the radius of convergence is dictated by this implicit equation, okay? And the way to do this, you do some Puiseux expansion, there are singularity analysis of this, and you get all of this. Okay. So, and if you apply this now to count the limit laws for the corresponding limit laws, what you will get is that now for the Gibbs model, okay, we have a Q here, and in these three different areas, you will get three different limit laws. Okay, so in the subcritical regime, so in this case here, you get a Boltzmann distribution. So Boltzmann distribution being defined like with this parameter of this parameter. So it's defined like this. So the Boltzmann distribution associated to a function g, here g prime, but this is just this quantity. And the specific case of this, for example, if the function which is there is, for example, the quasi-inverse one, a sequence of something, or a power of the sequence, then this Boltzmann distribution becomes something which is famous, which is a negative binomial distribution. So many cases of negative binomial distributions, which are popping up in the literature, in fact, are just avatar of these more general cases here with something which is, in fact, a Boltzmann distribution. Okay, now let's go to the critical case. In the critical case, what we get, here we get that if you renormalize your statistics by n to the lambda h being the critical exponent of h, then you converge to a general, two parameters Mittag-Defer distribution. Okay, the density of this distribution is given by this one. One famous specific case of this is, so if you take just a sequence of guy behaving like a square root, you get the Rayleigh distribution. So there was some work by Michel Soria and Michel Mota many years ago on this case. Okay, and then in the supercritical case, what we get, you get that you converge to a Gaussian distribution with linear mean and variance. Okay, and we can also prove that in the variance, this big ugly coefficient, but which is explicit and full generality, is never zero. Okay, and one more stuff which can be said on those cases, in which way behaves the mean. So in this case, the mean is just a constant. So when it is subcritical, you have an explicit value for the mean, and it will be like this. In the critical case, the mean behaves like n to the lambda h, and Gaussian case, linear. Okay, so the tools to prove this theorem are, okay, the previous lemma, you play a little bit with those expressions, you recycle the part of what we did for in the previous AofA. We use methods of moments, which I will comment, and then you get that it is a Mittag-Defer distribution in this case. And for the last case, it's nice application of the Wong's quasi-power theorem, which is known to lead to Gaussian stuff. So let me comment just a little bit on the moments problem here. So for our schemes, in more generality, even with the mutuality factor at the end, at the critical value, we have a convergence to a 3-parameter Mittag-Defer distribution, which is a distribution which is characterized by those moments here. So the classical tools to prove this is the Frechet-Shoah theorem. So if you have your moments for a given n, which are converging to something, to the moments, to some values, MR, to the values of some moments of some distribution, you can conclude from this that you have a convergence in distribution if one important condition is fulfilled, if the distribution, the limiting distribution here, is uniquely determined by its moments. Okay? And there is some famous criteria to decide of this. So due to Karleman, And the criteria depends on the support of the distribution. So if the support of your distribution is real positive or the full real or a compact interval, you have different criteria. And in your case, we have a positive support here. And so you just have to check, is it the case that not the square root, but the 1/2 are square roots of these guys when you do the sum here? Is it plus infinity? So you just use Stirling and you prove that, oh, yes, indeed, it is plus infinity. So the Mittag-Leffler distribution with 3 parameters is indeed characterized by its moments. And this, you prove it by doing some singularity analysis, recurrences, and so on. So this is a way to prove this type of stuff. So I have to mention also here that there is a lot of distributions which have those type of shapes. So there is a survey by Svante Jansson which calls them distributions with moments of gamma type. But I think that one of the lessons of this talk is that among those, the Mittag-Leffler distribution that we have here is really universal and is really the distribution which is popping up for critical compositions. So the limit laws, they are at infinity. Is it possible to see this phase transition between these different limit laws when we are at finite n? So here, I draw the distribution of the number of returns to 0 in some lattice path of length n. Okay, and I give a weight q to the number of zeros, so Gibbs weight. So if q equals 1, for those guys, I get this curve. Q equals the critical Q is this one, and Q equals 3. So you already see that for a small value of n, we begin to see the phase transition. This one at when you send n to plus infinity will converge to this Boltzmann discrete distribution. This guy here will converge to the Mittag-Leffler distribution, and this guy here will converge, will shift like this with linear mean to a Gaussian. Okay. So let's give some applications, example of this. So for example, if you consider the number of peak points in some permutations with the forbidden pattern. So here you have permutations avoiding the pattern 3, 2, 1. So it is like in the talk by Wenge, to forbid a pattern is not consecutive. It could be spread in the stuff. So here you cannot find 3 points in these guys, in these distributions, which are decreasing. It's 3 to 1 forbidden permutation avoiding the 3 to 1 pattern. Okay, and there is one nice generating function for those objects, which was obtained by Vela and Elizalde for other set of patterns here, which is this one. Okay, so this is the generating function. And in fact, by playing a little bit with generating function, it's possible to rewrite it in the shape of a composition. It's possible to rewrite it like this. So it's a sequence of H where H behaves like this. So it is fitting our scheme. It's a composition. You can say that it is what is more critical compositions. And therefore, you directly get that the number of fixed ones under the Gibbs model will satisfy the negative binomial Mittag-Leffler, which is simplifying to a Rayleigh distribution in this case, and then the Gaussian case. So this was also considered by in an article by Shelley Cavada and Panzo. Okay, another example. Let's do the returns to 0 in Dick and Motzkin paths. So Dick, okay, we have those jumps. Motzkin, we had also the horizontal jump, and we consider bridges and excursions. Bridges, you start at 0, you go anywhere, you end at 0, and excursions are bridges which are constrained to be non-negative. Okay. And in fact, for all of them, you can see here that, okay, they are compositions. They are composition of recurrence, and they are critical compositions. So therefore, you can apply your schemes, and you get the Q when under the Gibbs measure, you get those phase transitions again, with a location of the phase transitions which can be computed and which is different for the different lattice paths. Okay. Another example. Consider walks in the equator plane which are accepting those steps. So those ones are called diagonal walks, or this set of steps, they are called diabolo walks, or this one for the chess lover, the king walks, okay, where you can move to any adjacent cell. Okay, and so you move like this in your equator plane, and you are putting a weight q to the number of contacts with one axis. And you are asking, okay, what will be the distribution of this? Okay, in fact, it's possible to show that it is, again, a composition scheme like we had before. So we have this phase transition, negative binomial before the critical value, Rayleigh at the critical value, Gaussian after. Another example. So the two watermelons with the walks, the friendly two watermelons. So here, the walks, they can touch, but they cannot cross. So it's a model which was considered by Christian Kratenthaler, Tony Gutmann, and Xavier Viennot many years ago, and even previously by other people in physical mechanics, which was also analyzed by Valery Reutner. And so it's possible to get the generating function for those guys. It satisfies the composition scheme. So we apply your theorem, and the number of contacts with the weight, Gibbs weight, will follow also those phase transitions. Okay, and let's now go back to the initial question by Christian Kratenthaler. So in the model by Christian, so exact the definition of the M watermelons. So you have like this M lattice paths, which are above the one above the other. Okay, and the starting altitude and the ending altitude are forced here by this condition. And what is more, there is a wall. The wall means that you cannot go below zero. Okay, there are the objects. So here you have the three watermelons with a wall, legs 24, and we have 7 contacts with the x-axis. Okay, so you put the weight q to the number of axes. What will be the distribution for this one? So we have the Boltzmann, Mittag-Leffler, Gaussian phase transition. And in this case, if you replace the critical exponent by the exact value, the Boltzmann simplifies to a negative binomial. The Mittag-Leffler simplifies to a chi distribution, and the Gaussian is the Gaussian. What is the proof for this? So the formula, the big formula which I mentioned before, which was obtained by Christian, comes from applying jeu de Catin and for sure determinants, Gessel, Viennot, and Lensstrom. And in fact, there is a nice phenomenon. So you have to go to the article to see it, is that this big formula with the product, in fact, can be simplified to this very simple formula. In fact, the generating function, the associated generating function is of very simple shape. You see very combinatorial and so on, but we don't have an explanation of this. It comes from a big simplification, and this is really calling for bijective proofs, but we have none. And Christian is also quite an expert in bijective proofs. So the mystery. Okay, but we don't need this bijective proof. The shape of the generating function is this one. So it is a composition. So therefore, we can apply the phase transition schemes and we get this. Okay, last example. So let's do return to zero in some colored walks. Okay, so those objects, in fact, are related to integer multi-compositions, which are objects which are introduced by George Andrews some years ago and considered also by people in physics. And so they are lattice paths like this, for which the first one will have a color up to a given return to zero. Then you change color. Then you change color again, so m times. And at the end, you have a Q which is black. Okay, so these are your objects. Okay, and then if you are counting the statistics number of returns to zero with a Gibbs weight, then okay, it's again the composition schemes, and you will get, depending on the number of colors, the half normal distribution, the absolute value of the Gaussian distribution, half normal distribution, the Rayleigh distribution, the derivative of the Gaussian, the Maxwell distribution, or in full generality, when you have m colors, Mittag-Leffler distribution, those parameters. Okay, so in conclusion, so this unifies the analysis of the Gibbs model under the umbrella of composition schemes. It explains the universality for many phase transitions, which were in some cases observed for example, for the average or something like this. It is establishing, I think, the new universal limit laws. I mean, the importance of Boltzmann distribution as limit laws and Mittag-Leffler distribution, now I think is clear. So you can remember the shape of the Mittag-Leffler distribution. You just remember, okay, it's a product of gamma and with this shape. So if you get something of this shape, you should, oh, there should be some Mittag-Leffler behind, possibly. Okay, so you can apply this to a variety of examples. And what you get at the end is those type of phase transitions, critical value, where you have the Mittag-Leffler distributions, subcritical Boltzmann discrete distribution, and above the Gaussian distributions. Okay.
Questions for Cyril?
Sure, funny talk. So on page 10, I noticed that there are several lambdas with no subscripts. I was wondering, what are they?
Lambda with no subscripts. I think that the font is sometimes perhaps not easy, and the location of the subscripts is not very nice. No, it should be lambda with subscripts everywhere. So you remember one slide?
Page 10.
10? Yeah. 1 bar of chocolate?
Oh, I see.
I don't see.
No, I see. Yeah. Oh, and then on page 16. So, wait, let me see. So like for the last formula, the denominator is d of z pure. Why is it not d of z pure u?
Here? Well, when you do this this product, you will see that it is this. Yeah.
Okay, but like for the numerator, the u stays.
Yes, there's a u here. Yes. So here, when you extract the coefficient of z, then so this depends on z and u. Q is a real number. So you extract this quantity. So you get a real positive value. And when you extract this here, Q is a real number. So it just depends on Z. And so you get a real number divided by real number, which is exactly this probability here.
Thank you.
Another very quick question. Challenge.
Thanks, Cyril, for the presentation. So at some point you considered Deakin and Motzkin bridges and excursions that ends, both of them ends on 0. If we consider prefixes of these objects, it means that the last point can be anywhere. Does it change drastically the situation, or we have the same type of behaviors?
Alors, I forgot if we have them in the article or not. So it will be what we call sometimes meanders. Those objects. This is the keyword for it. Is it the case that it will be critical compositions there? Well, it could depend on the statistics.
What I can say on this, basically, you shift often the limit law, because sometimes this is responsible then for a factor m of z in the composition scheme. Because sometimes you can then think of it like a bridge until one point.
Yeah,
and out or not.
Yeah.
And this is just change. This is a factor m of z. And this factor m of z is then sometimes influencing the limit law. So you see a difference.
Yeah.
So
For example, for bridges, the returns, in a sense, just for bridges, the returns is radially distributed, but the returns for walks, sorry, if you have like whatever, if you do something, it's half normal distributed. And something like this.
So it will be related, in fact, to these slides. And you have a sequence of return to 0, then your Q, M. So the critical exponent of M will interplay, will give this. But we have to check if the stuff that you want to study is critical or not. If it's critical, it will satisfy this stuff.